So these are notes from the Algebros, Flipped Math, and I just thought this was a little more concise, but there's only a couple pages of this. And then we do have, I printed off some slideshow pages. These are some of the slideshow pages because there's more information here. So a vector is really just what we call a directed line segment. That's all a vector is. It's a directed line segment. And a vector has this point right here, which is called an initial point. And then the end of the vector where the arrow is called the terminal point, where it ends. And every vector, we can put it on an XY axis. So any vector can be put in like a polar, this vector could be placed on a polar coordinate system or a rectangular coordinate system. Okay, so wherever this is, I mean, this vector could literally go anywhere. It could be slapped anywhere on an XY axis. And that means that it could have an initial ordered pair, like this could be an ordered pair, like an x1 comma y1. And then this could be like an x2 comma y2, like they could be ordered pairs. And if I want to find the magnitude of it, the magnitude means the length of the vector. You will see that in every like different, I don't know, system, I guess you can call these like the different worlds of mathematics. Okay, so like one world is the Cartesian, the rectangular world, and then there's polar world. Okay, there's vector world. There's series world. There's all these different systems that we use to explain basically the same exact things. All right, they all have their own vocabulary that goes with them. So when we're in vector world, vector land, a directed line segment is called a vector. The beginning point is called the initial point. The ending of it is called a terminal point. In geometry, we would have just called this a ray, right? The magnitude in vector land means how long it is. So a vector, usually the variables we use for vectors are v or w. V and w are common ones, okay? So v and w. And the way we, u, v, and w are all similar ones. And a vector's, the way we write it, we'll talk about component form in a minute, I guess, but its length, so here's a vector. The way we write its length or call it magnitude is we put double vertical lines around it. The magnitude means the length of a vector. So now if you really consider the length of this vector that has a beginning point at x1, y1 and a terminal point at x2, y2, like if I want to find out how long it is, I'm really just going to use the distance formula. I'm going to take the square root, and this is if I have ordered pairs that represent the beginning and the end. I'm going to take x2 minus x1, the difference in the x's, and square them. And then add the distance between the y's, y2 minus y1 squared. And if you think about this distance here, this is actually called, like this distance from here to here, this is the x component. This is the, like this distance from here to here, and then this is this distance, and I've literally just made this into a right triangle. So this distance is the x component, or the x side of this vector, and this is the y component, the distance I would go in the y direction. So we denote in vector, just vector v. In geometry, we might have written v with a little like that ray symbol over it. Okay, but here we just call it vector v, and the way, when we write it like this comma this with these pointy arrows, like vector a comma b, This is saying the x component is A, and the y component is B. So like, then when I write a vector in component form, our assumption is that it always begins at the origin, and this tells us how far to go in the x direction to get to the end of the vector, and this tells us how far to go in the y direction, and then we get to the ending point of the vector. Every vector is just the hypotenuse of some right triangle. That is literally all a vector is. We stuck an arrow at the end. Okay, so the magnitude of a vector when it's written in component form is the square root of a squared plus b squared, which means that a is the distant difference in the x's, and b is the difference between the y's. Like, you really just need to understand that we literally have the same picture that we just had in converting polar to rectangular coordinates. We have a right triangle. Because now we're going to talk about, like, you know, what if I know the angle of this vector and its length? All right, so here's our example that goes with this problem. I want to find the magnitude of the vector -4, 8. Okay? To find its magnitude, I am literally just going to take the square root of -4 squared plus 8 squared. Well, a negative squared is a positive, so that's 16 plus 64 under the square root. That's the square root of 80. And if they asked you to estimate it, you'd give me a decimal. If they don't say estimate it, then you need to simplify it. 80 is the same as 16 times 5, so this would be 4 radical 5 as the exact answer. Now, if I wanted to graph this vector, I would start at the origin and go -1, 2, 3, 4 in the x direction, and up 1, 2, 3, 4, 5, 6, 7, 8 in the y direction. And then I would draw a vector from the origin to here, and I would just, let's call this vector W, and label that vector W. Now remember, vectors, we can actually now, this could also be on like a r comma theta. So this vector U could be over r around theta, where U is like the radius, and we still have like the x component and the y component, and this is like r. So since we honestly have the same picture we did from polar to rectangular coordinates, the x coordinate of a vector, if I know the length of the vector, if I know r, the length, the magnitude of the vector, and the angle it makes with the positive x-axis, its angle in standard position. Remember, standard position angles start here and go counterclockwise. X is equal to r times the cosine of theta, and y is equal to r times the sine of theta. Same formulas we had converting polar to rectangular. So I want to find the components of the vector U if I know that its magnitude is 15 and its angle is 60 degrees. Well, the x component of the vector is going to be 15 times the cosine of 60, and this is in degrees, so if you're going to use a calculator, you make sure it's in degrees. I'm just going to use my unit circle. My unit circle has radians and degrees, and then comma 15 times the sine of 60, and now I will have the component form of the vector. So the cosine of 60 is 1/2, so 15 times 1/2 is 15 halves. And the sine of 60, that should say 60, I wrote theta first. The sine of 60 is radical 3 over 2, so this would be 15 radical 3 over 2 is the y component. The pointy brackets tell you it is a vector. Okay, so that's how you know you're dealing with a vector. Pointy brackets tell you it's a vector. All right, now we want to find the components of this vector. If the magnitude is 6 and the angle is 160. Okay, so the angle of 160 is going to be like way over here, and a magnitude of 6 is shorter than that one. So this would be like 160, 6. Now, so the component form of this, and I draw a picture of it, because the component form should be a negative x and a positive y. So that's just a way for me to double check that I have the right component form when I'm done. So the x component will be 6 times the cosine of 60, or 160, comma, 6 times the sine of 160. Now, 160 is not an angle measure on my unit circle, so I'm just going to get a calculator out and calculate. I need you to get a calculator out. I'm fresh out of calculators over here, so make sure you're in degrees. And you would just probably round to the nearest hundred. So I got my x component to be like negative 5.64, which is good because that's what I anticipated it should be negative. And then 6 times the sine of 160 should be positive. Whoops. And that's 2.05. Okay, so things that aren't unit circle values, unit circle angles, using a calculator is just fine. So something that might be mentioned earlier, like if I have a vector that has like components a comma b, that would be a vector that is like over a and up b. If I take the opposite side of each of these, negative a comma negative b, it's a vector that is the same length but just in the opposite direction. Okay, so like the opposite signs make the whole vector go the opposite direction. All right, a scalar is like a constant, okay, but a scalar is like a multiplier, a numerical multiplier. Okay, so we say we're going to multiply by a scalar, so like we want to make the vector 4 times longer, or 1/5 as long. We multiply each component by that scalar. So this is like a scalar times a vector. We just distribute the scalar. That's all this is saying. So all you're doing is multiplying by the scalar. Okay, now we're going to draw both vectors and compare. So first of all, this is my vector 3 comma negative 2. So 1, 2, 3, negative 2. There's my vector 3 comma negative 2. There's vector, we'll call it A because it's part A. Twice that vector is 6 comma negative 4. So then if I draw that vector, 6 comma negative 4, so I go over 1, 2, 3, 4, 5, 6, negative 1, 2, 3, 4, and I draw that vector right. Notice it's in the same exact direction as the first one, it's just twice as long. All right, so now I've got that same vector, and now I'm going to multiply it by negative 2. I get the vector negative 6 comma positive 4. That vector, negative 6, positive 4, is that vector right there. It is the same direction. Notice how like they make a 180-degree angle between them. It's like I just extended the line and put an arrow on the end of it. So what happens with the direction of the vector when you multiply it by a scalar? Nothing. Nothing happens. unless you multiply it by a negative scalar. Then it switches the direction. Pretty easy so far? Okay, vector addition or subtraction. Vector, we call it addition, but vector addition or subtraction. I mean, vector subtraction. It's just like A1 minus A2, comma B1 minus B2. It's the same thing, okay? But vector subtraction, an addition graphically is important, especially for application type problems. I don't know if in AP Pre-Calc they got into this or if you took regular Pre-Calc. I know I always taught this because it has to do with trigonometry as well. But when you do vector addition, the answer to vector addition, we're just always going to call it addition, because subtraction, you just multiply by -1 and then add. The answer to vector addition is called the resultant. That's new vocabulary. The answer to vector addition is called the resultant, because some questions might say, what is the resultant vector when this happens? So vector addition we can do graphically or algebraically. Now algebraically is easy. I'm going to do algebraically first. So algebraically, I just add the x components, so 3 plus 2, comma, add the y components, -2 plus 5, and my vector addition is 5, comma 3. So the resultant vector, the result of adding these two vectors is 5, comma 3. Now, graphically, I'm going to do it up here. Graphically, I'm going to use a method called tip to tail to help me figure out where my solution begins and ends. So the tip to tail, I'm going to start by drawing vector 1, which is this. And you always start your first vector at the origin. So vector 1 is 1, 2, 3, comma, -2. So there's my vector 1. Now, wherever that vector ends is where my next vector has to begin. So now my next vector has to begin at that point that I just landed on. So I have to think this is my new origin. This is my new origin, and from here I'm going to go forward 2 and up 5. So when you do vector addition, it's like you draw a vector and then you start over and pretend the end of that vector is your new origin. And now I'm going to go forward 1, 2 and up 1, 2, 3, 4, 5. And that is this vector. So I put the tip of this one on the tail of the first one. Wherever one vector ends, that's where my second vector that I'm adding ends. Now, how do I get my answer vector? Okay. So I drew vector 1 first, and then on the end of it, I start vector 2, and then my answer goes from the origin to the end of this one. My answer goes from the origin to the end of vector 2. So my answer vector is from here to here. Now, if I match up that answer vector, which should be at 1, 2, 3, 4, 5, comma, 1, 2, 3, yeah, that's exactly what I got algebraically. The vector I end up with using graphical addition should land in the same position from the origin as if I do it algebraically. Does that make sense? Okay. Now, I might draw a picture up here. So first of all, this is just a question. You try. Find the magnitude of vector u. All right, well, there's vector u. The magnitude of vector u is going to be the square root of 4 squared plus 2 squared, or the square root of 20, which simplifies to 2 radical 5. Have you done this before? Like, does it seem familiar as you're doing it? Okay. Now I need to take 2 times vector u minus 3 times vector v. Well, follow the order of operations here. I first do the multiplication. Take the scalar, take the number 2 times each component of vector u, and twice vector u becomes 8 comma 4. I am actually going to put an addition sign here because I'm going to take vector v times negative 3. So I take each component of vector v times negative 3 times 2 for the first one, and so this becomes positive 9 comma negative 15. And then I add those together. I add the x components and get 17. Add the y components, get negative 11. And this is my resultant vector, which is literally just like saying this answer to addition. Okay? Now, we've already done a couple of these. I'll review. Okay, so find the components. The components are the x component and the y component. So those formulas are all based on the right triangle. X is r, or the magnitude of the vector, times the cosine of the angle. And the y component is the length or magnitude of the vector times the sine of the angle. And you would just use a calculator. I actually would just leave it like this, probably, unless I really needed to know. All right, we're going to move on. That was the easy stuff. So this is 11.1, still not 11.2. Now, a concept that we'll use a lot, unit vectors, okay? Unit vectors, and there will be several slides on this. A unit vector is just a vector that's a unit long, and you can take any vector and make it its magnitude 1 unit long by just taking each component, the vector itself, and take each component divided by its length. Okay, so it just says find the unit vector for the vector 3 comma 5. Well, I'm just going to take each component and divide it by the magnitude of the vector. So the magnitude of vector 3 comma 5 is what I find first, which is the square root of 9 plus 25, or the square root of 34. All I have to do to find the unit vector, sometimes we just say the unit vector is u, for this vector is I'm going to take each component and divide it by the square root of 34. And there's my unit vector. So the way the problem is usually worded is find a unit vector in the direction of this vector. Well, if you keep this same vector and make it a unit vector, it's automatically in the same direction. Now, I'm not even going to rationalize these. But if you're doing some of the problems from the book, you're going to see that maybe they wrote this as 3 radical 34 over 34. It's the same thing. I just saved some, I don't know, lead or something. Now, verify. Verify it's a unit long. Well, let me find the magnitude of this unit vector that I just wrote. That would be the square root of 3 over radical 34 squared plus 5 over radical 34 squared. Please don't get a calculator out. This is not hard. So 3 squared is 9. The square root of 34 squared is 34. 5 squared is 25. The square root of 34 squared is 34. Add these two fractions that now have a common denominator, And you get 34 out of 34, which is 1, and the square root of 1 is 1. It's a unit long. Now, I think these are actually like a little farther ahead. We'll revisit these. So an important calculation you can make with vectors is called the dot product. And the dot product of two vectors will probably be written u dot v. That's how we write the dot product. And it's important that you recognize that this is the dot product, and it is very specific. The dot product is either like you multiply the x components, you multiply the y components, and then you add them together. Or another formula for the dot product, so this is one formula for it. Another formula for the dot product is the magnitude of vector A times the magnitude of the second vector times the cosine of the angle between them. So these are just two different ways to find the dot product. Now, coincidentally, we can find the angle between two vectors by rearranging this formula and saying that the cosine of the angle between two vectors is the dot product. I'm going to call them vectors A and B. Sorry, I should call these vectors A and B here. Vector A and vector B. The dot product of these two vectors, they use U and V in the formulas later, but since they have this A and B, it's the dot product of the vectors divided by the product of their magnitudes. Okay, so if I'm given these two vectors, I know they're vectors because they have pointy brackets. I could find the angle between them by saying the cosine of theta, the cosine of the angle between them is the dot product of the vectors. The dot product, you multiply the x components and you multiply the y components and then you add them together. A dot product is a number. And then you're going to divide by the magnitude of the first vector times the magnitude of the second vector. And I'm just saying square, square, add them. All right, so the dot product will be negative 6 plus 24, which is 18. And this is the square root of 25 times the square root of 40. Well, I know the square root of 25 is 5. And the square root of 40 is like the square root of 4 times 10, or 2 radical 10. So on the bottom is really 10 radical 10. Now, how do you suppose I would find the angle from here? How would I get theta by itself? Yep. Yeah, inverse cosine. So theta is going to be the angle whose cosine is 18 divided by, begin parentheses, 10 square root of 10. Like you have to begin the parentheses here. Okay, so I'm gonna give my angle in degrees here. This is like in vectors we can use degrees again because a lot of times we're trying to understand what the angle means. So I'm going to go second cosine 18 divided by begin parentheses 10 second square root of 10. If I don't do that, it's going to take the cosine of just 18 divided by 10 and then multiply that answer by the square root of 10. I don't want to do that. All right, and that gives me 55.3 degrees. So theta is approximately 55.3 degrees. And it's 12:19. Oh, that is a lovely picture. Where do you suppose that is? Colorado? All right. We'll skip that one for now. We'll see this again. Okay, when two vectors are perpendicular, okay, like I said, it's the vocabulary that you have to get straight. Instead of saying perpendicular when we're dealing with vectors, if this vector is perpendicular to this vector, we call them orthogonal, if they make a 90-degree angle with each other. In that case, their dot product equals 0. Okay, so now I'm going to back up to this one. So if I want to find the angle between these two vectors, the cosine of theta is the dot product of these. So 5 times 6 is 30, plus negative 3 times 10 is negative 30, divided by the magnitude of each, the product of the magnitude of each. Now, I kind of wasted my time. The dot product, what's 30 plus negative 30? 0. So 0 divided by anything is what? 0. So even if I figured this out, even if I figured out what this answer was, it wouldn't matter. 0 divided by whatever. I'm solving the problem to find the angle. What angle has a cosine of 0? Or theta is the inverse cosine of 0, which is 90 degrees. Your calculator will tell you. So when the dot product is 0, it tells you that your two vectors make a 90-degree angle with each other. They're perpendicular, or in vector language, orthogonal. Now, the rest of these go to the slideshow, but they're like other things from 11.1 and a little bit of 11.2. And they're just extra things to know. So generally the length of the sum of two vectors is not equal to the sum of their lengths. So to see this, consider vectors u and v. With u and v as two sides of a triangle. The length of the third side is the magnitude of the sum. And it's like the triangle inequality that you learned in geometry. So the magnitude of the sum is always less than or equal to the sum of the magnitudes. Okay, that's just kind of nice to know. Now, the unit vectors, I told you how to write things in terms of a unit vector, but when we're dealing in vector land, we always like to refer to what we call standard unit vectors. And standard unit vectors allow us to rewrite every vector in standard unit vector form, okay? So there are, in 2 dimensions, there are 2 standard unit vectors. They are vectors that are 1 unit long along the x and the y axis. Now this is easy. This is really easy. Don't make it hard. So the vector along the x-axis that is 1 unit long is vector, it's called vector I. So vector I is 1, 0. You go over 1 unit and you don't go up at all. Vector j, so this is the x unit vector. And j is the y unit vector. And it is the ordered pair 0, 1, or the vector. Don't go left or right, just go up 1. And these are pictures of them. Now, because of this, I can take any vector and rewrite it. So I could take vector 2, -3, and write it in terms of unit vector. So this is just a basic vector. In terms of unit vectors, this would be written as 2i minus 3j. So any vector in component form can be written in terms of unit vectors by taking the x component and saying times I, and then plus, and since the second one is negative, plus the y component times j. These two are equivalent statements, and I should be able to go back and forth between these two. And you're like, well, how? How can I do that? Well, let's say, like, these are equivalent. The vector 2 comma negative 3 is the same as 2i minus 3j. So let's say I had 5i plus 6j. What vector would that be? Well, that's 5 comma 6. But why? Right? Why? Well, remember, we just defined vectors I. Vector I is 1 comma 0. And vector j is 0 comma 1.
I do.
So if I replace the I with 1, 0 and j with 0, 1, then I do the scalar multiplication. So 5 times this vector is 5 comma 0 plus 6 times both of these components. And then when I add these two vectors together, 5 plus 0 is 5, 0 plus 6 is 6. And they'll also refer to this as a linear combination of I and j. Rewriting a vector in terms of unit vectors is called writing it as a linear combination of I and j. And so a lot of times you'll see problems that might say, you know, find the dot product of these two vectors. 6i minus 2j and 4i plus 3j. Find the dot product of these two vectors. And you're like, well, I'm confused. Well, don't be confused, just rewrite them in the normal component form. So like this vector is actually 6 comma negative 2, and this vector is 4 comma 3, and then it's easy to find the dot product. I multiply the x components and get 24, add the product of the y components, and I get 18 for my dot product. And I provided another example here. So let u be the vector with initial, now some problems start out like this is a good problem. So you know the ordered pair that vector u starts at and the ending point. So this is kind of an important thing. So vector u has the initial point at 2 comma negative 5 and the terminal ordered pair at negative 1, 3. To write this in component form, I have to take the x's end minus beginning. You always take the terminal point minus the initial point. The terminal x minus the initial x. End minus beginning. That's, okay, so to write a vector from ordered pairs, you take end minus beginning. So negative 1 minus 2, comma, the ending y minus the beginning y. 3 minus negative 5. So vector u is negative 3 comma 8. You cannot just subtract in any order. It's always end minus beginning. All right, so I'm going to skip this next example for now, and we're just going to talk a tiny bit about 3 dimensions. I just want to save that example for later. So we're just going to talk about 3 dimensions, vectors in 3 dimensions in the 3-dimensional coordinate system. If you want to see these bigger, you can pull up the whole slideshow. Like this is just from the slideshow you have access to on Canvas. So the 3D coordinate system, the x-axis actually ends up being, sorry, that's wrong. So the x-axis is this one that kind of is coming out at you. This is the positive x and the negative x. And the y-axis is horizontal. This is the positive y and the negative y. And then the z-axis is up and down. And they're showing that here. And it's made up of different 3 intersecting planes. And so they just go through how to graph a point in space. There's 8 octants. And there's ordered triples X, Y, Z. And you're not going to be spending a lot of time graphing a bunch of order. You might be asked to graph a couple things. But if you're typically going to graph a point in 3 space, that's actually my, yeah. Okay, so you always start at the origin. So if I wanted to graph, like, I'm just going to graph an easy point, 3, 4, 5. Okay, so X, Y, Z, ordered triple, alphabetical order. You do start at the origin, and this is the only point, the only number you're actually going to go out to 3. So you're going to go out a distance of 3 because that's the only one. Now, if I'm going to go 4 in the y direction, I don't go all the way over here to 4. Because remember, we're trying to make a 3-dimensional dot on a flat space. So this is what we call a perspective drawing. The reason the x-axis is at an angle is to draw your eye back to make you think that it's going back. Have you taken 3D art? Have you ever looked at a picture and it's like, oh my gosh, I feel like I could step into it. It's because they draw things at angles so that it draws your eye to the back, okay? So we only go out, this is the only one you go exactly to that mark. This is a distance of 4 in the y direction. So I literally get out like a little piece of paper, and I say, all right, well, how far is 4 along the y-axis? 1, 2, 3, 4. That's the distance I need to go over from wherever I ended up here. So I ended up here. From here, I need to go that distance in the y direction, parallel to that axis. And that's where I go next. So this is 4 in the direction of y. So like imagine now I am out in this front room, I'm in the middle of this front room. So like if we started in this corner here, like back here, if we started in this corner, we would have gone out 3 and now we're somewhere out here. And now we need to go up a distance of 5 from there. So now I go to my z-axis and I say, well, how far up is 5 from the origin? And I go 1 to 5, that's a distance of 5. And then I find where I ended this, and from there I go straight up, parallel to my z-axis, a distance of 5, and that is where we end up. And it looks weird, okay, here, 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 and that point actually would create like a box. So like if I went, this should be 3, 4, 4, I would go up 5, like that one dot, I can create a box. But it's not, you're not like graphing things in 3D or anything like that. So now, some of these things are just equations. Like you can get an equation of a sphere. So a sphere is a 3-dimensional circle. So wherever this origin is, this is in an ordered triple. That's the center of the sphere. And then the sphere has some radius, okay, some radius distance from the center to any point on the sphere. And this is just the equation of the sphere. Some of these things are just, nice to know things. All right, in three-dimensional space, you can find the midpoint of a line segment. Okay, so even in 3 space, you know, you have a dot floating in a room somewhere and another dot, you can still draw a line between them. And that line, you can find out how long the line is, like the distance formula. I don't think that's, oh, I might have skipped the distance formula. So we can write that with the midpoint. Okay, so like the distance between these 2 ordered triples, x1, y1, z1, okay, so this is the midpoint. The midpoint is the average of the x's. Add the x's, divide by 2. Add the y's, divide by 2. Add the z's, divide by 2. The distance is like the distance formula in 2 dimensions. It's going to be x2 minus x1 squared plus y2 minus y1 squared. And then you just have a z component, plus z2 minus z1 squared. Now, the rest of this, vectors in space, a vector in space just has 3, it just has 3 components in the vector. And now that we have 3 dimensions, we have the I unit vector, let's see, the I unit vector in the x direction, the j unit vector in the y direction, and now the z unit vector is called k, ijk, alphabetical order, x, y, z, I, j, k. So you have the x unit vector, the y unit vector, the z unit vector. The x unit vector is called I, j, and then k. But since they're in 3 dimensions, the x unit vector is 1, 0, 0. The y unit vector is 0, 1, 0. And the z unit vector is called k, 0, 0, 1. So any vector in 3 space can be written in terms of I, j, and k. This would be 2i plus 0j minus 3k. But many times, since if any component has a 0 in front of it, you would actually just write 2i minus 3k. And then to find a vector in 3 space from 2 points, it's like they show you here, n minus beginning. Component form. From 2 ordered triples, you always take end minus beginning for each component. And they have that formula right here. All right, last 2 little bits, and then we're stopping with vectors. So summary of vectors in space. This gives you like formulas. They're all similar to the formulas from 2 space. Okay, and one new thing: parallel vectors in 3 dimensions. Like in 2 dimensions, it's easy. Like parallel vectors are vectors that go in the same direction, okay? Yeah, they would be parallel to each other. But in 3-dimensional space, I could have 2 vectors, like one might seem to be going this way, and one might seem to be going this way, but they could still be parallel in space. Okay, so they could be going like it appears 2 different directions, but they still would never cross. And the way you tell that 2 vectors are parallel in 3 dimensions is if one vector is a multiple of the other. Okay? if you can take one vector multiply it by any number and end up with the other vector, and the number could be a positive number, a negative number, it can be a fraction, and you can end up with the other vector, then they are parallel. So like if I had vectors -1, 2, 4, and then vector 3, -6, -12, and I wanted to know if they were parallel, I would just have to say, well, is there anything I can do to this vector? Like you have to multiply like everything by the same number and end up with this. Or here to here. So if I start with this, I say, well, like how are all of these related? Are they related? Are all these related? Well, yeah, if I took this and this and this and divided all of them by 3, 3 divided by 3 is 1, 6 divided by 3 is 2, 12 divided by 4 is, or 12 divided by 3 is 4, but the signs are different. So if I just took this one and times -1/3, like divide by 3, same as times -1/3, if I did that, then I would get -1, +2, +4, which is that vector, so these are parallel. Yes, they are, because one is a scalar multiple of the other. Now, the only thing we really have, like we've already actually covered these pages, but we'll review them next time, not next time, but after the quiz. We have a word problem to talk about from 11.1, but that should pretty well cover 11.1 and 11.2. So the people who aren't here will be responsible for watching this video while we take, before whatever, Friday or something. So I do want to spend the last little bit, first of all, seeing if you have questions for me. And let me just start by saying, can you find a first and second derivative in parametric form? You think so? Okay, can you find a derivative in polar form? Can you set up an integral to find area within like a certain section or like of a pedal or something? Just set up the integral. Okay. Could you write could you find the points of horizontal and vertical tangency? Okay. So let me give you a couple problems to practice at the board then, because I can sit here all day and talk, but let's see. So in your book, go to the chapter 10 review. Use notes. Can you find the arc length in polar or parametric form? Maybe. Okay. Now, I will give you those formulas. I'll give you the arc length. I won't make you find the area of the surface of revolution, but you will have to find arc length in either polar or parametric. I'll give you those formulas.
How is the quiz set up? Like, what are the number of questions about what?
It's not long. Like, it's literally a quiz. There might be 7 questions on it.
Tops? 7 tops?
Well, okay, so you have to, like, convert points and equations from polar to rectangular. You'll have to find a derivative, first and second derivative, slope and concavity.
Yeah.
You'll have to find a derivative in polar form, set up an area.
Okay.
I mean, that's about it.
We don't have to find the area of the surface or whatever? Yeah, the area of surface.
I'll just make you find arc length.
What pages are we looking at here?
All right, you're just looking at the
wait, arc length is
little s.
area of the surface.
Area of the surface is capital S. So page 747. 747, you should be able to do problems 33 and 35. So 33 and 35, or no, never mind, not those. Well, you should be able to graph them. You should be able to do 33, 35, but what I want you to do is, I want you to do 45 and 48. 45 and 48 from the review. Or 45 or 48, okay? Either one, 45 or 48. Just making sure. The derivative for polar form, you have to change, you have to use those conversions. So you're going to have to, so polar derivatives, if you have a function r equals f of theta, you have to first convert this into parametric form. So x is r cosine theta, and y is r sine theta. So like, and there's a formula, so dy over dx is going to be this, the derivative of this in terms of theta. And so like the derivative of and remember this r is your function. So you're going to have whatever your r is, so first times derivative of the second, plus second times derivative of that. And then on the bottom is the derivative of the x part, which is first, times derivative of the second, plus second times the derivative of the r. So like the derivative in polar form you have, because you're finding dy over dx, and if you just find that derivative there, it's not dy over dx. So this is the formula for polar derivatives, where your r is the problem you're given.
How come it gives you the parameter? Do you have to like eliminate it?
What?
It gives you the...
It says after you find the first and second derivative, then you need to plug that number in. So when they say find it at that value, so you find the derivative. Remember, derivative tells you slope.
Yeah.
And you only want this, like the derivative is the formula for the slope. So if you want the slope at a certain point, you have to put that in.
Plug it in and then
Yes, but that's after you find the derivative. After, because if you just plug 1 in for t, you're just finding the ordered pair, not the
actual
not the
value.
Oh my God!
Scream at max volume and as low of a voice as you can muster. You. Yes.
Genesis.
Okay,
Now the second derivative, remember, that's a little weirder.
Oh yeah, it's only the top one. You only do y, right? You leave x the same, and then you find the second derivative of y.
No, you find the derivative of the first